Welcome to Study Loop.
For this problem on the topic of electromagnetic induction, we are given a rectangular circuit that is moved at a constant velocity into, through, and then out of a uniform magnetic field as shown in the figure. We want to find the magnitude and direction of the current that is induced in the circuit, as it is firstly going into the magnetic field, and then secondly totally within the magnetic field and still moving, and finally moving out of the magnetic field. We finally want to sketch a graph of the current in the circuit as a function of time for the three cases. Now, when the loop is entering or leaving the region of the magnetic field, the flux through it is changing and there's an induced EMF. The magnitude of this induced EMF, epsilon, is equal to the magnetic field strength times the length L times the speed of the circuit V. Now, the length L we know is 75 centimeters or 0.75 meters. Now, when the loop is totally within the field, the flux through the loop is not changing, so there's no induced EMF. Now, let's look at part A. We know that the current that is induced is equal to the induced EMF over the resistance. And this is BLV over R. So we know the magnetic field strength to be 1.25 Teslas. The length of the circuit is 0.75 meters, and it's moving at a constant speed of 3 meters per second. All of this divided by the resistance of 12.5 ohms. So we get the induced current to be 0.225 amperes. So we have the magnitude of the current that is induced. Now, the magnetic field through the loop is directed out of the page, and it's increasing. So the magnetic field of the induced current is into the page, inside the loop, and so the induced current is clockwise. So we have the magnitude and direction of the induced current when the circuit is going into the magnetic field. Next, we want to know the magnitude and direction of the current when the circuit is totally in the magnetic field but still moving. Now, the flux is not changing in this case, so both the induced EMF and the induced current are zero. There are no induced current or induced EMF. And finally, when the circuit is moving out of the magnetic field, we have the current again is epsilon over R, which, like above, is 0.225 amperes. Now, this time the magnetic field through the loop is directed out of the page and is decreasing. So the magnetic field of the current that is induced is out of the page inside the loop, and hence the induced current is counterclockwise. And so we have the magnitude and the direction for the induced current when the circuit is moving out of the page, or out of the magnetic field rather. Now finally for D, we want to draw a sketch of the current versus time, which looks as follows. So here we have a sketch of the current versus time, and if we take the clockwise currents to be positive, at t is equal to 0, the loop is entering the field. It is totally in the field at time t is equal to ta, and begins to move out of the field at time t equals tb. Now the graph looks as follows. As we can see, the current is positive when the t is less than or equal to ta, and negative between tb and the final time.